This is the problem on the cannon, and it says a cannon of mass 5,800 kilograms is rigidly bolted to the earth, so it can recoil only by a negligible amount. The cannon fires an 85.0 kilogram shell horizontally with an initial velocity of plus 551 meters per second. Suppose the cannon is then unbolted from the earth and no external force hinders it to recoil. What would be the velocity of a shell fired by this loose cannon? And in parentheses, hint, in both cases assume that the burning gunpowder imparts the same kinetic energy to the system. Okay, here I got these little clip art from the software here. I actually thought that this one was kind of cool because it kind of shows this cannon on a train wagon, and it actually has labeled the recoil of the whole thing. So, but anyway, I thought it was kind of cool. I'm actually going to put this one aside here, just down here, just outside the picture, I guess, or maybe just inside the picture, outside. And I'm going to use this old-fashioned cannon and this Cannonball, and I'm going to draw some ground here. There we go, and I'm going to grab these two here, and I'm going to bolt them down the cannon, that is. So here's that's supposed to be a bolt, and then there's a bolt. Okay, let's look at what we have given and what they're looking for. What they eventually will be looking for is the velocity of the cannonball when it's shot unbolted. They give us the velocity of the cannonball as it is being shot while it's bolted, which means that actually we have to do the problem twice. So I'm going to copy this one. Let's see, and then when I move this down here, I'm positively running out of space at some point. Okay, so let's see what we have given. We have given the mass of the cannonball. We have given the mass of the cannon. And we have given the initial velocities of both, and this is for the bolted cannon. The initial velocities before anything happens are 0, nothing moves, so we have this one here. And they actually, for the first part where it's bolted down, we actually have the velocity given, the final velocity of the cannonball. And then the first part, they're actually not looking for anything, but what they're looking for instead is, let me move this down here, or up I guess, is that again we have this given here, this given here, this given here, this given here. For the second part with the unbolted one, they're asking for the velocity of the cannonball when it's unbolted. So this is the unbolted part, and this one here is the bolted part. Okay, let's see what we get. Conservation of momentum. So for the bolted cannon, before anything happens and then after it's being fired. So before, what we have is 0, no momentum. After it's being fired, it's m1 times the final velocity of the cannonball plus m2 times the final velocity of the cannon. However, remember that it's bolted down to the ground, and so as the cannonball goes forward, sorry about my strange looking arrow, as going forward, there is a recoil on the cannon, but it's bolted down to the ground, and that means that the ground absorbs that recoil. What is the ground? Well, the ground is the Earth. So this one actually is the Earth's mass. Now, we could calculate We could calculate what this velocity is here, but imagine we have 85 kilograms here and we have in the neighborhood of 10 to the 24 kilograms here. So for the velocity here, we're going to come up with 10 to the -3 or something like that meters per second, a totally negligible amount because that recoil really doesn't matter a whole lot to the Earth. And then we actually can't do anything with this particular number. So what's going on here? What can we actually do with this kind of information that's given up here in the first part of the problem? Well, look at the hint. It says in both cases assume that the burning gunpowder imports the same kinetic energy to the system. So what I'm going to do now is I'm going to write down what the kinetic energy is. The kinetic energy after it's being shot is 1/2 m1 vf1 squared of the cannonball, and so this would be 85 kilograms times what was it again, 551 meters per second squared, and so on, and then plus the kinetic energy here, so m2, and again this would be the Earth's mass times vf2 squared. Now in our heads, notice that this one is a huge mass, 10 to the 24, but in our heads I just calculated the VF2 as being in the neighborhood of like 10 to the -23. But now, which means that these two actually kind of take care of each other. However, this one is squared, and so what I have here is 10 to the 24 times roughly 10 to the -46, and I have such a small kinetic energy in the neighborhood of like, I don't know, 10 to the -22, that this one here is virtually 0. So what that actually means is that for a bolted cannon, the kinetic energy goes all into the cannonball and virtually none of it in the into the cannon that's bolted to the ground. Interestingly enough, though, I didn't mean to put that little thingy on there. Interestingly enough, though, is that as it has to recoil with the Earth, that this one here is actually not negligible. Not the way we're going to calculate it, but it's actually the same as this one here. So the recoil is still there, the action forces are still there, so the momentum is there, but the energy is unequally distributed and so small for the bolted cannon that it's negligible. For the unbolted cannon, that's not the case. The kinetic energy, if we calculate it, it still comes out pretty small for the unbolted cannon, but it's there, it's not negligible, and we will have a different outcome for the cannonball. Anyway, what I should write here, before and after, so this is the kinetic energy after. What is it before? Well, nothing is moving before. That means that the kinetic energy before is 0, but where does it come from? Well, they mentioned the gunpowder, and so that implies it's the chemical energy that is stored in the gunpowder. So I would write here in a later chapter we come up with that we use a Q for heat, and that of course is, once the gunpowder starts burning, that's the heat that it exerts, and then it wants to expand, and that of course pushes the cannonball out. So that's why I rather write a Q here for the initial energy. Okay. So this is the first part here. Actually, what we calculate here is the energy that the gunpowder sets free, that is then virtually totally absorbed by the cannonball, and so that's 1/2 times 85 kilograms. That's a cannonball, that's about 180 pounds, times the final velocity is given as 551, and I have to square that, and I come up with 12.9 million joules. So 12.9 megajoules, or times 10 to the 6 joules.